Okay, so hi everyone. So Timothé Rouzé, I'm a master student, and I'll present the work I've done during my end of study internship at the Bonsai team from Lille. It's a work I've done mainly with Igor Martaillan, who managed more the theory behind what we did, and I was more the dev for this project. So a bit of an introduction first. As you may know, the SRA database has been growing increasingly in the past years, and we've now around 72 petabases that are stored on the database. And such amount of data is really hard or impossible to analyze as such now. And we need new methods to analyze massive amounts of genomic data. And we're interesting about comparing data sets. So for example, you've got a metagenome. You want to compare it with reference genomes to know what's present in this metagenome. And for this, we can use indexes such as Jacquard index, where the principle is just to take the intersection between the two data sets you've got and to divide it by the union of these data sets. And you will obtain a Jacquard index. And what's cool with this Jacquard index is that you can approximate it really accurately by just selecting a few samples of each of your two data sets. And this is where we place our work. So there are several methods to perform such operations on k-mers. One classic one is bottom bin hash that is implemented in MASH. So on the your left side, you've got your k-mers, x0, x1, x2, etc. You will hash them with a hash function, and you will select only the smallest hashes of k-mers to construct your output sketch. There's other methods such as scale min hash that is implemented in SourMesh, where you have your k-mers, you hash them, and you will select every hash of k-mers that are inferior to a threshold R here. And these are a bit different because on one side you take a set number of k-mer on your output sketch, where on the other side you take a fraction of your input k-mers in the output sketch. And it implies quite some differences. So when, for example, the data sets you want to analyze are very different in sizes or in content, the Jacquard index approximation is not reliable anymore. So this is where scale size sketching, where you select a fraction of your input data, is interesting because it keeps the consistency of the Jacquard index when you are in such cases. So here, for example, you've got an example of fixed size sketching. Sorry. Where on the left you will select two elements from each of your data sets, which are the one on the left. And you will miss the similarity that you should have found between these two, where is the 12 there. On the right is an example of the same data sets, and you perform scale size sketching on them. And so you will select, for example, a third of each k-mers from each data set. We'll end up with 1 for the smallest one and 4 with the biggest one. And you will find the similarity that you should have found. So a bit of theory now. Usually these methods are applied on k-mers. We apply these methods on super k-mers and on minimizers. So a minimizer is a small m-mer of a k-mer according to some order. So on this example, it's according to the lexicographical order, but in general, we use random orders or anything else. And a super k-mer is a run of consecutive k-mers that share the same minimizer. So the yellow bars there show you the different super k-mers that we can construct from this sequence. And you can note that, for example, the first one, CTG AAA TGC, is a maximal super k-mer because you see that the first k-mer that is part of the super k-mer has its minimizer on the right-hand side of its sequence, and the last k-mer has its minimizer on the left-hand side on its sequence. So you couldn't go further away with this minimizer at this position to construct a super k-mer. It's important to note the width parameter, which sets the maximal size for a super k-mer, which is found by having k minus m plus 1. So here it would be 4, and you can check that. It works. And so we will use minimizers as a footprint to perform our subsampling, our selection k-mers on super k-mers. And what we want is a sparse minimizer set. So here's the formula for the density. It's the number of selected minimizers divided by the total numbers of m-mers that we see in our sequence. And for example, if we take again the lexicographical order, we will end up with 5 different minimizers if we decide to keep everything, and as many super k-mers. If we change a bit the order and we have a better one, we will represent the same data by having to save only 2 minimizers, which is better because and you can note that we will maximize the size of our super k-mers. So there's a relationship between low density and longer super k-mers. The optimal density is known. It's 1 divided by W. And when you use a random order, the expected density is 2 divided by W plus 1. And we wanted to do better than that. So we interested ourselves to universal heating sets, which is a set of m-mers such that every one of W consecutive m-mers has at least one element of S. So you are guaranteed to find a m-mer if it's present in the sequence in your output. And the density lower bound for UHS is 1.5 divided by W plus 1. So that's a bit better than random order. And we're wondering, can we cross this lower bound by relaxing some constraints? So by, for example, using guaranteeing the presence of m-mer if it exists with a certain probability. And that goes back to the scaled size sketching, kind of. So you will select a fraction of the minimizers with according to a threshold T. And if our minimizers are smaller than T, we call them small minimizers, and this is the minimizers that will be present in our output sketch. With that, we were able to calculate a density upper bound, which is here, and we are happy with it because when f equals 1, we go back to the random order expected density. But as f goes towards tends to zero, most k-mers will not be covered, and it's not really meaningful. So we tried to improve that, and we ended up with this formula, which I won't read, but here's a graph that shows the same thing. And we can note that when f equals 1, so we are at a density factor of 2. And once it crosses 0.8, the 1.5 barrier from the UHS is crossed already. So we are quite happy with that. And it approaches the optimal density as f tends towards 0. So we're quite happy here. As I said, the density is related to the size of your super k-mers. And we wanted to be able to calculate the proportion of maximal super k-mers that we could get. And so here it is. When f equals 1, you have roughly 25% of super k-mers. You can expect roughly 25% of maximal super k-mers in your output sketch. And it goes towards 100% when f tends towards 0. We compared this with the tool we've developed, SuperSampler. And we obtained these 2 nice graphs. So on the left here, it's a comparison with the theoretical upper bound that we calculated in orange. And in blue, it's the it's SuperSampler when it performs subsampling. We see that it follows quite well what we expected, so we were quite happy with that. And for the proportion of maximal super-k-mers, it performs better than what we expected, and we still haven't really figured out why. So if you have any idea, we are happy to talk about it later. And one last thing related to these two parameters, it's the cost in bits per k-mers. And we've seen that it decreases really quickly towards 5 here on this figure, but the second point here is a subsampling rate of 10. So it's if you keep only 1 k-mer out of 10, in general you use a subsampling rate of more like 1,000. So it should continue to go down towards 4 or 5 bits per k-mer, which we're really happy about. I talk more about how we developed SuperSampler to be really optimized when performing comparisons. So here is how the sketches are created. So we have our sequence, we slide through it, constructed by checking every minimizers of every k-mer we encounter. And if the minimizer is below our threshold, we will keep it in our output sketch with the super k-mer associated with this minimizer. Sometimes you'll have the same minimizer at different points of your sequence. And when this happens, such as with the one on the left and the one on the right, we store them in the same bucket in our output sketch, so that every super k-mers sharing the same minimizers are stored together. And this will help us improving the comparison, the computational time for comparison. Because so if we want to compare a query sketch Q with references, for example, so A, B, C, etc., we'll have our sketches, which are the colored boxes. You can see them as k-mers, and when they share the same color, it's because they share the same minimizer. Okay. So in SourMash, which is the state of the art for scale size sketching now, you will check every k-mer of your output sketch of your query sketch. Sorry. And you will compare it with every reference that you have. In SuperSampler, as they are stored by according to their minimizers, you just have to check if the green minimizer, for example, is present in your reference sketches. And if it's present, then you will compare the k-mers that are stored in this bucket. But for example, with the pink or gray minimizers that are on the bottom right here, they are not present in the query. So it means that we don't have to check them because we know that the k-mers inside these buckets are not present in our query. So a bit of results to finish. So we've compared SuperSampler with SourMash. On here, it's on RefSeq data, so it's really dissimilar genomes. We've subsampled and compared 2024 genomes. So we were 50 times, in general, 50 times faster than SourMash. Our sketches are lighter than those of SourMash, and we were generally using less RAM. And then we've compared with a less friendly data set for us, which are 1024 Salmonella genomes, which are really similar between them. So our optimization by not looking the buckets if the minimizers are not present is not working as much, but we were still faster than SourMash, so we were happy with that. And the other two metrics didn't move quite a lot. So yeah, I'm done. If you want to have more insight about the theory behind our work, Igor, I think, would be pleased to talk with you at the poster session. It's poster number 123. And if you want to chat with me after that, we can talk also. I also have a poster. Thank you.
All right, questions? Hi, thanks for the interesting talk. So what's the intuition behind why it's better than minimizer? Like why directly downsampling chimeras using minimizers, right? So for you use a small minimizer and then sampling chimera, right? Yeah. So why it's better?
Why is it better to use super chimeras instead of chimeras?
Yes.
Yeah, okay. It's because if I show you a super chimera here. Okay, so here, for example, you've got your chimeras, okay? And if we represent them using minimizers that are friendly with us, which is generally the case, we will represent the super chimera as one sequence. So on the right would be TGT, TGT, GCT, only once. Whereas you would have to write the 4 chimeras that compose these super chimeras, so 4 times. And you would have a redundancy of your information that is saved in your sketches, where we skip this redundancy to just have the sequence.
So can I summarize because your methods have a lower density?
Sorry?
Can I summarize the reason as your method has a lower density?
Yeah.
Okay.